All right? So if I increase the pH, in other words, I add hydroxide to the solution, which way is this going to shift, left or right? Somebody's nodding their head. It's going to shift towards reactant, right?
Yeah.
Correct? It's going to shift to the left, towards reactant, because I'm adding a product. Okay? What happens if I lower the pH, if I add hydronium? Okay? Hydronium reacts with the strongest base in solution. The strongest base in solution is obviously hydroxide. I react with hydroxide. I'm removing a product. If I remove a product, I'm going to shift towards products. That's directly from the Chatelier's principle. All right? So, these problems are actually looking a little bit like buffer problems, and the fact that you do a stoichiometry step prior, looks like a titration problem. You do a stoichiometry step prior to applying the equilibrium conditions.
Okay.
All right? So, anything that will react with one of the products is going to affect the solubility. All right. Reactions that involve basic anions, which are conjugate bases of weak acids, will be directly affected through the hydrolysis reaction. So barium fluoride, get barium and fluoride. Fluoride is a conjugate base of hydrofluoric acid. Therefore, fluoride is a weak base. It will ionize with water. So if I add proton to this, the hydronium is going to react with the fluoride and cause this to shift to the right because I'm removing a product here. All right? And I might ask you, what is the solubility of barium fluoride in a solution that has this pH? Well, pH tells you the concentration of hydronium. You then have to neutralize all that. Then you have to do an equilibrium step with fluoride. And then you do another equilibrium step with barium fluoride. All right? So, complex ion formation. All right? We kind of lied to you several times this semester and last semester as to what's actually in solution. Metal ions can act as Lewis acids. Okay? Lewis acid is something that what? Accepts an electron pair, right? Electron pair acceptor. Can accept an electron pair from Lewis bases. And there's lots of Lewis bases. Here's a table of those. Now, notice what's happening here. On the reactant side, I have individual ions. On the product side here, I have something that looks really big and bulky and you would not expect to be soluble. But in fact, everything on this list has an aqueous for its phase. Okay? You've seen complex ions in solution. Last semester when you did the Le Chatelier, or I'm sorry, this semester when you did the Le Chatelier's lab, where you had cobalt tetrachloride and cobalt hexaqua cobalt. Remember you had the pink and the blue solution, right? Those were both complex ions, all right? And many complex ions do exist, and well, copper has several of them. Notice their formation constant here. They're huge. What that tells you is that, for example, if I have ammonia and silver in solution, they're going to seek one another out, and they're going to form diamino silver. All right? And it's going to remove some silver and some ammonia from solution. It has a Kf of 1.5 times 10 to the 7th. Meaning, the numerator is 1.5 times 10 to the 7th larger than the denominator. All right? These are very important techniques for getting rid of ions in solution. Now, this is still in solution, but it can sequester silver, for example, and keep it from reacting with other species. All right, at least for most concentrations. All right, we're not going to do any calculations for these because they are complex. Go figure. That's in the name. I just want you to be aware of them. In fact, one of the ways that we used to do the copper tartrate lab is we added sodium tartrate as a common ion. Well, copper tartrate is actually a complex ion, and instead of the solution decreasing in the amount of copper, it increased in the amount of copper tremendously, and we didn't like those results, so we got rid of copper that part of the lab when they changed from version 1 to version 2. Okay, so again, those are just things that affect solubility. We need to now be able to predict whether or not a precipitation reaction is going to occur. All right, so we need to understand what conditions a solution can be under. All right. The solution, we learned last semester that we can have an unsaturated solution, meaning the solution can hold more solute particles. We also learned last semester about a saturated solution, which meant that we had solid at the bottom of the beaker and we had some of the ions in solution. Well, now we know that that is an equilibrium between the ions in solution and the solid. All right? And then we also learned last semester that we had what's called a supersaturated solution, which meant that we had more solute dissolved than the solution should be able to carry. All right? And, well, ultimately it's going to crash out of solution eventually. All right? So we have to be able to quantitatively now predict what's going to happen. Okay? So to predict that, like we do with any equilibrium process, we compute Q, reaction quotient, and we compare it to K. All right? We did this back in chapter 15. You've been tested over this. Yeah, I know that was before the snow days, but still, you've been tested over this. You know this already. All right. So all we do is compute Q using the initial ion, the initial ion concentration of all the ions. All right. So if Q is equal to K, then we're at equilibrium. That's what we learned back in chapter 15. If Q is equal to K, we're at equilibrium. What that means is that we have a saturated solution. That means that no additional precipitate forms. All right. We're at equilibrium because Q is equal to K. Now, if Q is less than K, we're not at equilibrium. But now, the reaction cannot go forward to achieve equilibrium because I have no more precipitate that can form. I have no more precipitate. Since I have no more precipitate, I can't go forward anymore. So that is a little bit of a difference. If I don't have enough solid present, I can't have a saturated solution. Okay? In other words, all of my solid could be dissolved in solution. In that case, Q will be less than K, meaning I can add more solid without a precipitate. And then finally, if Q is greater than K, that means I'm way too far towards products, a precipitate will occur, and it will continue to occur until I have removed enough material from solution that Q is equal to K again. Okay? All right. So let's do some problems. Okay. I have a 1 liter solution that contains 0.015 moles of sodium chloride. And I have I have 1 liters of solution. That solution has 0.01 moles of sodium chloride and 0.15 moles of lead nitrate. Will a precipitate form? Okay, first of all, let's treat this like it was a Gen Chem 1 solubility rules question. Okay? We need to know what's in solution. All right, so sodium chloride dissolves to give me sodium and chloride. All right. I need to know what's in solution. Plumbous nitrate dissolves to give me lead and nitrate. Now, in Chem 1, what we do is we swap partners. And we'd ask ourselves, are any of the new groupings that are formed, are any of them soluble? Are any of them insoluble compounds? Okay? So, we already know that sodium and chloride are soluble because they come in together as soluble. We know that lead nitrate is soluble because, well, all nitrates are soluble. So, we don't need to check the pairing that I already have written here. What I need to do is I need to look at the following pairings. You look at sodium nitrate. Did not bring another color. I'll borrow one. We need to ask ourselves, is sodium nitrate soluble? We also need to ask ourselves, is lead chloride soluble? In other words, we're swapping partners here. We're asking ourselves which What can precipitate? Well, what's the rule on column 1A metals? They're all soluble. Nitrate's also soluble. I guarantee you this is soluble. So the only thing I'm left with is asking myself, is lead chloride a soluble or insoluble compound, generally speaking, according to the guidelines? Halogens are soluble except for silver, mercury, and lead. So lead chloride would be the #1 candidate to precipitate here. All right? So, PbCl2 in equilibrium with Pb2 plus and 2 chlorides has a KSP equal to 2.4 times 10 to the minus 4th. And I now know my KSP formula. This is going to be the concentration of lead 2 plus times the concentration of chloride squared. Meaning, in order to answer this question, will it precipitate form? What I need to do is I need to know, technically since this is a K, these are equilibrium values. In order to know if I have if a precipitate's going to form here, I need to compute Q. Okay, well, in order to compute Q, I need my concentrations. Okay, well, concentration of chloride I have 1 liter of solution. That solution contains 0.015 moles of sodium chloride. 0.015 moles divided by 1.0 liters is a 0.015 molar chloride solution. Yes, the math is exceedingly easy here. Okay, my lead concentration, I have 0.15 moles of lead in 1 liter. So I have a 0.15 molar lead solution. These ions exist together in solution. They are the ions that go together to form my precipitate if my precipitate forms. I do not know that I'm at equilibrium, so I have to compute Q. So Q is going to be my actual lead concentration times my chloride concentration squared. It's the same functional form. And now I just plug and chug. 0.15 times 0.015 quantity squared, which is equal to, and I'm going to cheat, 3.8 times 10 to the minus 5. If I compare Q to K, Q less than or greater than K. Q is less than K, therefore, no precipitate forms. Even though, according to our solubility rules from last semester, you would have predicted, yeah, lead chloride precipitates. But remember, that was before we talked about concentrations. That was also before we learned about the concept of equilibrium. All right? This is the way you actually truly do the problem. Don't complain about the solubility guidelines. We simplify things. Okay. Another question. I mix 50 mils of 0.0010 molar calcium chloride with 50 mils of 0.010 molar sodium sulfate. Hey, this sounds an awful lot like the percent calcium carbonate lab in limestone that you did last semester in Gen Chem 1. Remember, you isolated your calcium in the last step by adding sodium sulfate. Actually, this is really truly the way we figure out what concentrations and what amounts to give you guys. All right, by doing calculations like this. Okay, so set up the problem pretty much the same way. We have to know what is in solution. Okay, on the exam, you're going to be given a table that has a bunch of solubility products on it. That's going to be in the possible use for information. Okay? I'm not going to tell you what compound is in solution, but I'm asking you if it's going to precipitate. You're going to have to calculate it on the exam. So you're going to have to use this same approach on the exam. Okay, so I have calcium chloride. Calcium chloride, it's already in solution. So we know it's soluble. It is an ionic compound, so it is a strong electrolyte, meaning it ionizes completely. Sodium sulfate, it's already in solution, so we know it's soluble. We also know that it's an ionic compound, meaning it ionizes completely. Again, we swap partners. I already know that calcium and chloride are soluble because I'm told that I have that in solution. I already know that sodium and sulfate are soluble because I'm given them in solution. The next thing I need to do is I need to compare the other two partners. Sodium chloride, soluble or insoluble? Soluble. Sodium is almost always a spectator. Meaning, the most obvious choice for a possible precipitate is my calcium sulfate. All right? So, calcium sulfate, for its solubility, is in equilibrium in water, calcium 2 plus, and SO4 2 minus. KSP is then going to be calcium concentration times the sulfate concentration, and it has a numeric value equal to 2.4 times 10 to the minus 5. And since we're doing Q calculations, I'm going to explicitly write a subscript EQ here on the concentrations to remind us that the only concentrations we can plug directly into K are those for the equilibrium concentration. We don't know if we're at equilibrium yet. We have to do that calculation. Okay, so from this, it tells me I need to calculate my concentration of calcium and my concentration of sulfate. All right, so calcium concentration is going to be equal to, I have 50 mils of 0.0010 molar. Of means times, like it did in junior high. So I have 50.0 milliliters of 0.0010 molar, and that's divided by, I'm adding 50 mils and 50 mils. So it's divided by 100 milliliters. Milliliters cancel, I'm left with molarity. And this is 5 times 10 to the minus 4. Molar calcium concentration. Okay? Next, sulfate. I have 50 mils of, which means times, 0.010 molar, and I'm diluting that to a total of 100 mils in my solution. Milliliters cancel, I'm left with molarity. This molarity is 5.0 times 10 to the minus 2 molar. Okay, well, I don't know if I'm in equilibrium, so I cannot plug this directly into K. I need to plug this into Q. Q has the same functional form. So I have, this is easy, I don't square anything. 5.0 times 10 to the minus 4 times 5.0 times 10 to the minus 2. And if I can do math in my head, that should be 2.5 times 10 to the minus 5. It is early. I was right. Okay, so Q is equal to 2.5 times 10 to the minus 5. I compare that to 2.4 times 10 to the minus 5. Q, even though just barely, Q is greater than KSP. Okay? Which means that my calcium sulfate will precipitate out of solution until Q becomes equal to KSP. All right? Not horribly difficult. All right? Similar to the calculations we did back there in chapter 15. All right? Okay. So we're going to mix a barium chloride in a sodium sulfate solution. KSP for barium sulfate is 1.1 times 10 to the minus 10. Will it precipitate form? Okay, same exact calculation again. Except for we're going to make this one more complicated. You knew a complication had to come, right? It's too easy. Now, for this particular problem, I'm telling you that KSP is barium sulfate. I'm giving you the KSP for barium sulfate, suggesting that barium sulfate is going to be the only thing that could possibly precipitate. And if I look at my counter ions, barium is partnered with chloride, so I have chloride in solution. Sulfate is partnered with sodium. I have sodium in solution. Do sodium and chloride ever really do anything in solution? No. All right. Not unless I have some other heavy metal present, like mercury, silver, or lead. All right. So barium sulfate is the thing that I'm interested in. All right. So in this particular case, I'm going to skip writing everything that's in solution, and I'm just going to talk about barium sulfate. Even though technically all that other stuff is going on, I just want to save some time here. KSP for this is 1.1 times 10 to the minus 10, which is equal to the barium concentration times the sulfate concentration, meaning I need to know, well, I need to calculate my barium and my sulfate concentration. Okay. The barium concentration, I have 50 mils of 0.0010 molar and 50 mils of, so it's going to be 100 mils. All right? So I have 50.0 milliliters of, meaning times, 0.0010 molar, divided by the total volume. In this case, it's 50 plus 50, which is 100. Milliliters cancel. It's a power of 10 thing. So this is 5.0 times 10 to the minus 4. Sulfate. I have 50.0 milliliters of the sodium sulfate. Its concentration is the same, 0.0010 molar. It's all in 100 mils. Hey, that worked out fortuitously. Now, question is, will it precipitate form? Okay, well, I got to calculate Q. Again, Q has the exact same functional form. So I can just plug in those values. I'm skipping a step now. (2.5 times 10 to the minus 7). Q is definitely greater than KSP, so a precipitate will form. Okay, why are you saying, why am I doing 3 problems like this identically? Well, here's one. Problem's not over. What the concentration of all ions in solution after any reaction, if a reaction occurs, is complete. In other words, after I precipitate everything, what is my concentration of all the ions in solution? Okay. Now, I know that a precipitate forms. That precipitate is going to continue to form until what? Q is equal to K. All right? So, I'm going to use my KSP expression. 1.1 times 10 to the minus 10 is equal to my barium concentration at equilibrium times my sulfate concentration, again at equilibrium. I don't know what its concentration is going to be at equilibrium. I know what its concentration is initially, and from the balanced chemical equation, I know that 1 mole of barium is going to disappear and 1 mole of sulfate is going to disappear. In other words, I'm going to do an ice table calculation. Okay? So let me go ahead and set that ice table up. Okay, my initial concentrations are going to be what I put into solution. 5.0 times 10 to the minus 4. 5.0 times 10 to the minus 4. Some precipitate is going to form, meaning this is going to be plus X. It's a solid, so its equilibrium doesn't, its concentration doesn't matter, but its stoichiometry does. Some barium sulfate will precipitate, meaning this is going to be minus X, this is going to be minus X. So I get 5.0 minus 4 to the minus 4 minus X. 5.0 times 10 to the minus 4 minus X. I plug those in over here. Yuck. We're back to solving quadratics. No, we don't have to solve a quadratic. What's the shortcut on this one?
Approximation.
It's a perfect square. Okay? This times that, it's the same thing, so this becomes a perfect square, meaning I can take the square root of both sides. So I have the square root of 1.1 times 10 to the minus 10 is equal to 5.0 times 10 to the minus 4 minus X, meaning X is going to be equal to 4.895 times 10 to the minus 4, and X is always going to be molar. Okay, now, what does that mean? Well, that tells me what is X. X is really how much barium sulfate is formed. Okay, so I could ask you how much solid is formed. Well, in this case, it's going to be X. I can tell you how many moles of barium sulfate are formed, because I know the total volume of my solution. All right, so the amount of barium sulfate that's formed is equal to X, is equal to 4.895 times 10 to the minus 4 molar. I multiply that times my total volume, which is 100 milliliters, which tells me that 4.9 times 10 to the minus 5 moles of barium sulfate are formed. Of course, I could use the molar mass of barium sulfate to convert that to grams if I wanted to. Okay? Now, it asks me for the concentration of all ions that are in solution. Okay? Well, concentration of barium is 5.0 is the 5.0 times 10 to the minus 4 minus the value of X, which X is 4.895 times 10 to the minus 4. That's equal to 1.1 times 10 to the minus 5 molar. By the way, the concentration of sulfate is equal to the same thing. Why? Because its initial value is also the same. 1.0 times 10 to the minus 5 molar. Now, chloride and sodium don't change. Okay? They don't change, but I didn't calculate their initial values. But we can do that. Barium chloride gives me 1 barium and 2 chlorides. Okay? I'm told the concentration of the barium chloride, meaning I am told this concentration. All right? But I get 2 moles of chloride, meaning this initial concentration for chloride should be twice the initial concentration of barium. All right? So chloride concentration is going to be equal to 2 times my 50 mils times 0.0010 molar divided by the total volume, which is 100 mils, meaning that chloride is going to be 1.0 times 10 to the minus 3rd molar. And it stays the same. Just simply twice this number. Okay? And the same thing is true for sodium. because it's Na2SO4, the sodium concentration is going to be 2 times the initial sulfate concentration. It would be 2 times 5 times 10 to the minus 4. So it's 1.0 times 10 to the minus third molar is the initial is the concentration part. Our sodium does not change. That's probably the worst case scenario for a calculation. Okay. Calculate the concentration of everything in solution. Calculate how much forms. All right. Okay. Now, one of the reasons why KSP is so important, particularly for environmental chemistry, because there are times when we want to get something out of solution, right? Because it's harmful to the environment, but we don't necessarily want to harm the environment any further by getting rid of a heavy metal, right? And sometimes what we need to do is we need to make sure that whatever contaminants are in our solution, we want to get them out one at a time. We don't necessarily want them to be combined with anything else. All right? So this is a process called fractional or selective precipitation. Separation of ions based upon differences in solubility. All right, so let's consider a generic solution that contains 2 cations, A and B. And I want to separate A and B. So what I'm going to do is I'm going to add another solution that contains an anion. We're going to call it precipitating ion, C minus. Right? And I'm just making this generic. 2 cations, A and B, and I'm going to react that with an anion, C. All the other things present in a solution of balanced charges are simply there as spectators. Right, now I can separate the 2 cations provided the KSP of the newly formed AC compound differs from the KSP of the newly formed compound BC. All right. So the compound that has the lower KSP will start to precipitate first, because the smaller the value of KSP, the more it favors reactants. The reactant is the solid, always for KSP. Right? So whichever one has a smaller value of KSP will precipitate first. Okay? I'm going to add my precipitating ion until Q of the more soluble compound is just less than its KSP. All right? What that's going to allow me to do is it's going to allow me to separate, to precipitate as much of the less soluble compound as I possibly can, at least using this particular process. Okay? Because as long as Q for the more soluble compound never reaches its K, the more soluble compound will not precipitate. Okay? So, question. Can I use silver nitrate to separate the ions in the anions of a solution that contains chloride, bromide, and iodide? Well, let's go back to the solubility guidelines. Silver nitrate is obviously soluble because nitrates are soluble. Okay? Halogens are soluble except for silver, mercury, and lead, meaning that Gen Chem 1 says, no, we can't because all 3 of these things are going to precipitate. What do you think we say in Gen Chem 2? We can, but what do we need to know? I need to know KSPs. There they are. 3 orders of magnitude difference. Meaning I'm probably going to be able to affect a fairly decent, now it's not going to be perfect, okay? One of the things that equilibrium tells us is that I can never drive a reaction 100% to completion. Why? Because some of my concentrations would be 0, meaning big K would blow up, or big K would go to 0. Big K is always positive. And actually, after this current exam, we'll learn exactly why that matters. And it turns out that something called Gibbs free energy has to go to infinity. All right. The point is, I'm not going to be able to get rid of all of the iodide by this process, but I can get rid of most of it. Actually, I can get rid of a tremendous amount of it. Okay? Now, in order to solve this problem, I actually need more information. I mean, I can solve this problem and answer this question. Yes, I can separate these. But what I actually need to know in order to make this quantitative is I need the concentration of all my ions. All right? So, let's solve a problem. Solution contains 0.1 molar barium and 0.1 molar strontium. You then add concentrated potassium chromate. I'm going to ignore volume changes. I'm going to make my life easier. It's not quite a titration. That would be worst case scenario. By the way, you can also do titrations based upon solubility. You can use the titration to calculate the solubility product if you want. All right. So, what I want to do is I want to try to separate barium and strontium. Okay? Question is, which ion will precipitate first? Which species will precipitate first? Will it be the barium chromate or will it be the strontium chromate? Now, in this case, all I have to do is look at KSP because the stoichiometry is the same, correct? It's a 1-to-1, meaning I have x squared is equal to the value of KSP for both of them, okay? So the molar solubilities are just going to be equal to the square root of KSPs. All right, so yes, the barium chromate will precipitate first. Okay? Now, question is, what concentration of chromate causes my barium chromate to start precipitating? All right. Well, in order to do that, I write down the KSP for barium chromate, which is 1.2 times 10 to the minus 10, and that has to be equal to the barium concentration times the chromate concentration at equilibrium. Now, when a problem says just causes it to start precipitating, that in essence tells you it's at equilibrium. Okay? So, I know my concentration of barium. All I need to now know is the concentration of chromate. So I'm going to solve this for the concentration of chromate at equilibrium, meaning right when the barium chromate starts to precipitate, is equal to the value of KSP divided by the barium concentration in solution, which is 0.1 molar. That's given to me. Okay, which means that chromate, when my concentration is 1.2 times 10 to the minus 9 in chromate, I first start precipitating barium chromate. All right? Not horrible. Notice all I did is I plugged in values into the KSP expression. What concentration of chromate causes the strontium chromate to start precipitating? I solve it the same way. KSP is equal to 3.5 times 10 to the minus 5 is equal to the strontium concentration. This is going to be considered at equilibrium because it's when it just starts to precipitate. So I'm going to have my concentration of chromate is equal to 3.5 times 10 to the minus 5 divided by my concentration of strontium, which is 0.10. So I have 3.5 times 10 to the minus 4th molar. Not a horrible problem. Fairly straightforward. As long as you understand the definition of equilibrium. As long as you understand that a precipitate first starts forming when equilibrium is established. Okay? Now, let's add silver nitrate slowly to a solution that has a 0.01 molar chromate and a 0.01 molar bromide concentration. Okay? Now, my stoichiometry is not the same. All right? Which means my first question, which is, what precipitates and what precipitates first, is a little bit more complicated. I actually have to do a calculation. All right, so I'm adding silver. I'm adding it slowly, which means its concentration is going to be, I'm basically going to be effectively doing a silver nitrate titration. I'm changing the silver concentration as I go. All other volumes are going to be constant. All right, so I need to know, both of them are going to precipitate because they both have very small values of KSP. The question is, which precipitates first? Okay, another way of asking that is, which precipitates at the lower value of the silver concentration? All right, so KSP for silver bromide is equal to 5 times 10 to the minus 13. Concentration of bromide is 0.01 molar, so the concentration of silver necessary to cause this to precipitate is 5.0. I'm just going to solve this for silver concentration. Okay, so it's 5 times 10 to the minus 13 divided by 0.010 molar. So the concentration of silver that's necessary here is 5.0 times 10 to the minus 10 molar. Minus 11, I lied. Okay. All right. The next one, actually the first one, the way I have it written here, I have silver. Now silver chromate. When I write the dissociation reaction for silver chromate, how many silvers do I get? 2. So this has to be silver squared times the concentration of chromate. Okay, that has a KSP equal to 1.1 times 10 to the minus 12. I solved this for the silver concentration, which is going to be 1.1 times 10 to the minus 12 divided by chromate, which is 0.010, and I take the square root of the whole thing. I'm skipping some algebra. This requires 1.05 times 10 to the minus 5 molar silver. So even though the KSPs look remarkably close to one another, the concentrations that are necessary to affect the precipitation are drastically different. All right. Remember I told you on the previous slide, we don't really need to worry about it because stoichiometry. It was the same, it's 1-to-1. This is showing you the reason why you do need to worry about it. You must take stoichiometry into consideration. All right? This is 6 orders of magnitude different. Okay? So what precipitates? Well, they both precipitate. Which precipitates first? The one that needs the least amount of silver, meaning silver bromide will precipitate first. When the more soluble species begins to precipitate, what is the bromide concentration in solution? Okay, so exactly what is this asking us? Okay? When the more soluble species, in this case the more soluble species is silver chromate. When silver chromate first starts to precipitate, how much of my bromide is left in solution? Okay? How are we going to do that? Well, we know what the silver concentration is when silver chromate first starts precipitating. It's 1.05 times 10 to the minus 5, right? All right. Well, I can plug that into the KSP for silver bromide and calculate the bromide concentration, right? Yes, if you say so. Okay. So. When the silver chromate first starts precipitating, the silver concentration is equal to 1.05, and I'm cheating on sig figs a little bit. 1.0 times 10 to the minus 5. So I want to know what is the bromide concentration when that happens. Well, that's easy enough. I plug into the KSP for silver bromide. Solve that for the bromide concentration. Get 5.0 times 10 to the minus 13 divided by 1.05 times 10 to the minus 5. And I'm going to get 4.8 times 10 to the minus 8 molar as the concentration of bromide when I first start causing the other substance to dissociate. Meaning, bromide started as 1 times 10 to the minus 2. I've changed the bromide concentration by almost 6 orders of magnitude. Okay? I've gone from, what, 10 parts per thousand to now 48 parts per billion. EPA would be happy with that. Well, I don't know if the EPA is ever happy. But the point is, we can drastically change the concentration, but we're not going to make it go all the way to 0. All right? Now, that actually concludes, right on time, Chapter 17. You have Chapter 14's lecture notes. I suggest you read about the first 3 sections of Chapter 14, and I will see you on Wednesday. I will not be in my office hours until 11 o'clock today, but I will be there from basically 11 till 4 if you need help. Thank you.